Hello everybody, today we're going to do 8.2, which is the reciprocal function family. It's mainly all about graphing reciprocal functions. So functions that model inverse variation have the form f of x equals a over x. And remember, f of x is just like y, so you can think of it as y equals a over x. And x cannot be 0, otherwise it would be undefined. They belong to a family whose parent is what's called the reciprocal function. Now, the reciprocal function's parent function is f of x equals 1 over x, or in other words, y equals 1 over x, and again, x cannot be 0, otherwise it would be undefined. Transformations of the parent reciprocal function include stretches, compressions or shrinks, reflections, and horizontal and vertical translations, which you have seen previously when we graphed the quadratics. We moved those left, right, up, down, stretched them, shrinked them, and we also did that with radical functions as well. So just real quick here, for a class party, the students will share the cost for the hall rental. Each student will also have to pay $8 for food. The cost of the hall rental is already graphed over here on the right, so you'll notice that, like, for example, if we look at the point 40, 6, the 40 represents the number of students, the 6 is the cost per student. That is just the cost of the hall rental. So the question is, what effect does the food cost have on the graph? Explain your reasonings. So if, in addition to the $6 that the person has to pay if there's 40 students, which the $6 is just the hall, you'd have to add another $8. So they would end up paying 6 plus 8 or 14. If there are 60 students, the hall costs $4, but in addition they would have to pay $8 for food, so they pay $12. So if you end up adding 8 to all the y values here, it ends up shifting this graph up vertically 8 units. And sorry for the background noise again. Apparently there's a loud helicopter going over my house right now. So this would be a shift up 8 units to take into account the $8 for food that every student needs to pay. Okay, so key concept. The general form of a member of the reciprocal function family is y equals a over x minus h plus k, where x cannot equal to h. The inverse variation functions y equals a over x. So if we have any number over x, kind of like in section 1, these ends up being stretches, shrinks, and reflections of the parent reciprocal function, depending on the value of a. When we graph something where it's just y equals a number over x, we'll make a t-chart, just like we did in section 1. So that graphing is not going to be any different, and you'll see that. The graph of the parent reciprocal function y equals 1 over x is shown at the right. And then I'll show you the specific points for that graph of the parent function y equals 1 over x in a later page of these notes. So the first example is going to be very similar to what we did in section 1. We want to graph y equals 12 over x here. Anytime you're graphing y equals a number over x, we're just going to make a t-chart to graph that. Then we're being asked to identify x and y intercepts and asymptotes of the graphs. It also asks you to state the domain and range of the function, which we're not going to talk about this year given the circumstances of teaching from away from the classroom. So do not worry about domain and range. You will not be tested on it. So let's go ahead and make a t-chart in order to graph y equals 12 over x. This is going to look very similar to section 1 when we graphed. Again, we're going to pick, just like in section 1, we're going to pick nice numbers that divide evenly into 12 in order to graph this. So some nice integer values that divide into 12 would be 1, 2, 3, 4, 6, and 12, and also their opposites. So -1, -2, -3, -4, -6, and -12. I'm going to take each of those x values and divide it into 12. So 12 divided by -12, my y value would be -1. 12 divided by -6, we get -2 out. 12 divided by -4 is -3. 12 divided by -3 is -4. 12 divided by negative 2 is negative 6. 12 divided by negative 1 is negative 12. And then the positives, 12 divided by 1 is 12. 12 divided by 2 is 6. 12 divided by 3 is 4. 12 divided by 4 is 3. 12 divided by 6 is 2, and 12 divided by 12 is 1. So this gives us quite a few points that we can plot to see what this graph looks like. I'm just going to pick a handful of the negative ones and then a handful of the positive ones to graph so we can get the idea of what this graph looks like. Notice that if I went by units of ones here, the negative 12 and negative 1 and 12 and 1 would not fit. So if you'd like, you can go by intervals of 2. I'm just going to leave those off of this graph. So I'm going to graph negative 6, negative 2. It's completely up to you. Whoops, my screen moved away on me there. So I'm just going to graph negative 6, negative 2. Negative 4, negative 3. Negative 3, negative 4, negative 2, negative 6. And then if we had more graph paper and you wanted to go by units of ones, you graph negative 12, negative 1, and negative 1, negative 12. That's what the graph would look like if we're going by units of ones in our third quadrant. And then I'm going to go ahead and graph 2, 6, 3, 4, 4, 3, and 6, 2. Again, you could graph 1, 12, and 12, 1 as well, but if I'm going by units of 1, it's not going to fit on this graph here. So there would be our graph of y equals 12 over x. Just like in 8.1, we have a vertical asymptote here at x equals 0. And we have a horizontal asymptote at y equals 0. And that'll be the case for any graph. That's y equals a number over x. We can't divide by 0, so it makes it undefined, hence those asymptotes. So there's our graph. It asks to identify the x and y intercepts and the asymptotes of the graph. So I already told you the asymptotes are vertical asymptote. In this example, is x equals 0. And our horizontal asymptote is y equals 0. As far as x and y intercepts, that's where our graph is going to cross the x and y axis. Well, here we never cross the x and y axis because we have asymptotes there, so there's none. X-intercept, none. It never crosses the x-axis. Y-intercept, none. And that will always be the case if we're graphing y equals any number divided by x. Go ahead and try example 2 now on your own. It's going to be the same directions, but you're going to do the graph of y equals 8 over x. And then go ahead and pause and try this. Okay, so let's go through this relatively quickly here. If we make our t-chart, you can see those values for y equals 8 over x. Just like the last one, you have vertical and horizontal asymptotes at x equals 0 and y equals 0. This time I chose to have my interval go by 2 on the graph, just to give you another example of how you can change the interval there. So I was able to fit all of the values on my graph here. It never crosses the x and y axis, so we have no x-intercept and no y-intercept. Now that's if you're graphing y equals a number over x. The next thing we're going to look at is if we want to graph using transformations. So if we look in this key concept here, again, our parent function is going to be the graph y equals 1 over x, which we're going to graph below in just a second. If you're graphing y equals a over x, so y equals a number over x, those are actually stretches and shrinks and reflections. But as far as graphing for our purposes, just make a t-chart anytime it's y equals a number over x. The next thing we're going to talk about is when we have to translate. So translation horizontal by h, vertical by k. This has a vertical asymptote of x equals h and a horizontal asymptote of y equals k. So if you look here, y equals 1 over x minus h plus k, that h is highlighted green. That ends up giving you your vertical asymptote, but be careful on that one, and you've seen this before. We're going to have to switch the sign because it's x minus h in the formula. So to find the actual vertical asymptote, you'd switch that sign. And then the k will give you a horizontal asymptote. It's always y equals k. You keep that sign. So I just put 2 quick examples off to the side for you. If you have y equals 1 over x minus 2 minus 3, their vertical asymptote is x equals 2. You're switching that sign. And your horizontal asymptote is y equals negative 3. You keep the sign there. If it was y equals 1 over x plus 2 plus 3, your vertical asymptote would be x equals negative 2. You're switching the sign of the denominator to get your vertical asymptote. And then your horizontal asymptote would be y equals 3. So you're keeping that sign to get the horizontal asymptote. Do not forget to write x equals and y equals. That's what makes these vertical and horizontal lines. If you just tell me 2, negative 3, 3, those are numbers and not asymptotes. Asymptotes means they're a line. Okay, you have to include x equals and y equals. This year we're not going to do the combined, that very last part of the key concept, so don't worry about that. Let's go ahead and quickly graph the parent function y equals 1 over x. So we're going to pick some x values to substitute in. This time the only even integers that divide into 1 are 1 and negative 1, which doesn't give us much information about the graph. So I picked some other x values to substitute in to find other y values for this graph here. So like I picked negative 2, negative 1, negative 1/2, 1/2, 1, and 2. If we substitute negative 2 in, our y value ends up being 1 over negative 2, or negative 1/2. If we substitute negative 1 in, 1 divided by negative 1 is negative 1. 1 divided by negative 1/2 is negative 2. 1 divided by 0 is undefined. This is what gives us that vertical asymptote of x equals 0. Now let's do the positives. 1 divided by 1/2 is 2. 1 divided by 1 is 1. And 1 divided by 2 is 1/2. Let's go ahead and plot these points here fairly quickly. We have negative 2, negative 1/2, negative 1, negative 1, negative 1/2, negative 2. 0 is undefined, so we have that vertical asymptote at x equals 0. And we also have the horizontal asymptote at y equals 0. And plotting the positives, we have 1/2, 2, 1, 1, 2, 1/2. Connect the points with a nice smooth curve. Get close to those asymptotes, but never cross them. And there's the graph of our parent function y equals 1 over x. Let me try that part again. A little crazy there. Okay, so anytime you're trying to graph the parent function, this is what you're going to graph, y equals 1 over x. Now we're going to go ahead and use this parent function, y equals 1 over x, to graph, on horizontal asymptote is always y equals 0, to graph things like this. In example 2, what is the graph of y equals 1 over x minus 4 plus 6? So the first thing we want to do is draw the asymptotes. Now remember up in the key concept, let me scroll back up there and show you. The highlighting up here of green and orange is what tells you those vertical and horizontal asymptotes. So the vertical asymptote is the opposite number of the denominator. The horizontal asymptote is going to be that number off to the right. So our vertical asymptote in this example is x equals positive 4, since we have that minus 4 on the denominator. And our horizontal asymptote is y equals the number off to the right, so positive 6. Okay, so you can go ahead and draw those asymptotes in. X equals 4 is the vertical line through when x is 4. And then our horizontal asymptote is y equals 6. There we go, our vertical and horizontal asymptotes. And then now I want to actually graph y equals 1 over x minus 4 plus 6. There's a couple ways to do this. The first way is to actually use the translation of it. So if you remember, this minus 4 right here actually means we're going to move our parent function to the right 4 units. And the plus 6 is a shift up 6 units. So if we were to take our parent function of y equals 1 over x right here, we would want to shift it to the right 4 and up 6, which is not super nice on the graph that we have here. So let me actually show you this over here. If I just copied and pasted this and I counted right 4, 1, 2, 3, 4, and then moved it up 6, 1, 2, 3, 4, 5, 6, it would give us the graph that we're looking for. And so one thing you can notice is that if you're doing this by hand and you can't just copy and paste it and move it around on an iPad like I am, that where your asymptotes meet, these points right here, I'm trying to write them in blue so you can see those 2 points right there. Whenever you're doing a transformation, they're always going to be one vertical and horizontal unit away from where the asymptotes meet. Okay, so that's another way you can think of this. Let me now move this back to where it should be. There it is. There's y equals 1 over x again. Okay, so what I was talking about on that previous screen is that I'm going to put points kind of catty corner from the intersection of the two asymptotes, and those points will always lie there. And then at that point you can just use your asymptotes. So get close to your asymptotes, go through that point that we know is always going to be there where our asymptotes lie. Same thing up here. I know it's going to get close to the asymptotes and it's going to go through that one point right there. So there would be the graph of y equals 1 over x minus 4 plus 6 using translations. Okay, go ahead and try the got it. You're going to graph y equals 1 over x plus 1 minus 2. Find out what the asymptotes are, and then graph either using translations or using the asymptotes. Alright, so let's go ahead and go through this one. Your vertical asymptote is going to be x equals -1. Your horizontal asymptote is y equals -2. So I drew those in pink. And then if you want to do a translation, you would go back to the parent function y equals 1 over x and move it left 1 and down 2. Well, I can show you that right now. So if I wanted to take this parent function on the previous screen, we can move it left 1 and down 2, and we end up at the graph for the got it. Okay. Now, obviously, again, if you can't physically pick it up and move it, You can use the fact that from where asymptotes meet, you're always going to be 1 away. Since we're not doing stretches and shrinks, this is always going to be the case. Put those points there and then just use the asymptotes to model the rest of your graph there. They just get close to the asymptotes and never cross them. And that is it for 8-2. So go ahead and get the bookwork done for that, and that'll be due on Friday, April 3rd. I hope you are all still doing well and keeping sane. Email me if you have any questions.